Hello, welcome to the presentation about particle value functions in imperfect information games. This is joint work with me, Vojtech Kovarik, and Viliam Lisy. Let me start with an example game of dark chess. Dark chess is just like standard chess, except that players do not have perfect observations about everything that happens on the chessboard. There are these shaded regions which note the squares that the players don't have perfect observations of, and they can only see the parts of the chessboard where their pieces can move to or where they can attack. A referee has a chessboard with exactly the same configuration and can see everything that is going on in the game, just like in a standard game of chess. He has like a perfect information version of the game, or like the perfect information perspective. And one more rule is that the players play to capture the king, not to put it into a checkmate. So let me show you a playthrough in this game. The players start in standard positions and they play for a number of moves. And the true game state can be seen only by the referee. It is not available to the players throughout the game. The players have only some partial perspective about of the game, and these different perspectives can be explained by the different possible game states that explain the observations that the players have. So, for example, the first player can think of all the different ways that the white player could have moved, like different pawn locations, or maybe moving the horse in different ways, moving the queen, and so on. And so can the other player. And the referee has the true game state available to him. When the player wants to reason about how the opponent sees the game, he has to reason about all the other possible perspectives over the game states that he can think he can be in. And the same applies to the opponent. So if we take this kind of recursive reasoning, then we arrive into a closure of the states that the players need to reason about, such that they know that the other player could be there and could be reasoning about these states as well. And this is called a common knowledge state, and it's a crucial component in the recent algorithms for solving or approximating Nash equilibrium strategies or max-min strategies in imperfect information games. And basically these algorithms use the common knowledge states to decompose the games. And for this decomposition, they use value functions. So they assign values to these states. And you may be familiar with the perfect information version of value functions, where you just assign a scalar to a single state. However, in imperfect information games, the situation is more complicated. So let me explain you briefly how it works. So instead of thinking about the individual game states, we'll consider only the perspectives, as I called them, or information states, or info states for short, of the players. And we will maintain beliefs over these info states. In other words, we'll maintain probabilities that what the players think, how each info state is likely to arrive due to their own course of action. So there is a policy pi that the player is using, and we're interested in the reach probability of that player to the individual info states that can arise within the common knowledge state. So the big S1 is the set of all info states in the common knowledge state, and similarly the situation is the same for the opponent. When we collect these beliefs and the common knowledge states, we call these public belief state. And for each of the info states, we track target values, counterfactual values for info states, and we'll denote them as V1 and V2. Note that these are sets of beliefs and sets of values. And a value function in imperfect information games is a mapping from the space of all possible public belief states to the space of all values. Now, the problem is that the sets of info states within the common knowledge state can grow exponentially large. So as you can imagine, if we keep on playing complicated games such as dark chess, the number of possible game states that the players need to reason about grows and grows the further deeper we are into the game, and so can the associated beliefs and values. Now, this poses a problem because existing value function approximations via neural networks use positional encoding of the inputs. So this means that we need to use exponentially large neural networks and learn exponentially large number of parameters. So these can be used only in games where the size of the common knowledge states is sufficiently small, and this is a very limited subclass of games. So we decided to tackle this fundamental problem and try to think about what can be done. So it's like all lost. Can we learn a value function? We observe that the full beliefs are needed only in a very special class of game, where basically the utilities that the players receive are very specifically balanced, and the only solution is like fully mixed equilibrium. And basically you can think of these games like example is matching pennies or rock, paper, scissors types of game. And there's a number of results that the support size, or this is related to the number of non-zero belief entries, the support sizes are actually can be small. So in random normal form games, the support size is logarithmic. And double oracle algorithms show that we can converge to small equilibria in a wide variety of real-world games. And the number of actions required for optimal play, even in games with huge action spaces, has been proven to be linear in the amount of hidden information. So the conclusion is that not all beliefs may be necessary for optimal play, but we don't necessarily know which ones are needed. So the idea is that maybe we can use a constant space representation of beliefs. We can try to compress these beliefs and simultaneously learn to regress to the target values. If the number of zero entries is really large, or alternatively saying the supports are small, then this compression actually can achieve perfect play, because we don't need to maintain zero values for unreachable info states. So the way how we do it is we maintain a set of representative histories in the common knowledge state we call particles. This is heavily inspired from POMDPs, where they solve a simpler task that we do. Their value functions predict scalars. However, we are mapping from sets of inputs to sets of outputs. So suppose that our memory budget allows only for a subset of the particles. We don't have exponentially large memory after all. So we trade off between the strategy quality and the computational efficiency. Here we show the diagram for the particle value function. We explain many more details in the paper, but the most important ones is that we can take arbitrary number of inputs modeled as set inputs. So these inputs correspond to each info state, which are described by some features and beliefs. These inputs after a transformation build up context. The transformation uses summation operation, similar to deep sets or multiple instance learning. The context is then used for regression, and then to compute the target values for each info state. The embedded regressed representation is then projected back for each info state, and this whole thing is learned via mean square error loss regression. We show that given unlimited amount of particles, a sufficiently large particle value function can represent a function identical to the positional value function. So given that we would use the exponentially large inputs and have these large neural networks, we can still learn the same thing. And we show experimental results that not only is our particle value function more general, but it can also slightly improve upon the performance of the existing positional value functions. So on the left, we show that we match, or it will be slightly improve on the exploitability of the positional value function. And on the right, you can see that when we use a fraction of the particles in the game, we can still maintain quite good exploitability. So for example, in Goofspiel, we can use only 30% of the histories or particles in the game and obtain a solution of similar quality. And in a LIDAC, when we decrease the fraction of the particles in the game, the exploitability decreases gracefully. So for future work, we'd like to learn these networks entirely from self-play training. In this work, we use the target values coming from an oracle. Then theoretical bounds for exploitability when using only a small number of particles could be established. And finally, apply to games such as Dark Chess. So thank you for your attention, and I'm happy to answer follow-up questions.